In this video, we'll talk about turbulent flow, and the equations that we use in this are based upon the same stuff you learned in the laminar flow lecture. The head loss equation is the generic equation or general equation, which depends upon the friction factor, the length over diameter ratio, and the velocity head, which is v squared over 2g. And this is the equation that you would use whether it's laminar flow or turbulent flow. Now, in case of laminar flow, we found out that the friction factor is 64 divided by Reynolds number. So what is the friction factor for turbulent flow? Turns out it's actually a pretty complex relationship. It's not even a relationship that can be described with a single equation. The friction factor in case of turbulent flow depends upon several variables in a non-linear manner, and those include the density, the dynamic viscosity, velocity, diameter, and the roughness factor. And we talked about this roughness factor, which depends upon how rough the surface, the inner surface of a pipe is, which is those small roughness undulations on the surface. And this relationship has been previously developed through empirical methods, and there are different equations for different types of pipes. So for smooth pipe flow, it's a nonlinear relationship like this one, and then we have the complete turbulent flow. Now there is a transitional zone, which we talked about before, that goes between the laminar and turbulent flow, where the flow actually oscillates between laminar and turbulent flow. Now, if you were to find friction factor for a given pipe of relative roughness E over D, you would have to solve this equation. It's actually quite hard to solve this equation in a straightforward manner. You have to either use a trial and error method or use some kind of numerical method to get the value of F. So we'll talk about that in the next lecture. In this lecture, you will use the Moody diagram to solve a couple of problems, and I will show you how to use. The Moody diagrams are the equations, these equations plotted on a graph paper. If you see that there are three variables: the friction factor, the relative roughness factor, which is roughness divided by the diameter, and the Reynolds number. So if we look at the plot of a Moody diagram, you have two y-axes and the x-axis. On the x-axis we plot the Reynolds number, and on the y-axis we have the friction factor. Now, for different roughness, relative roughness values, the curves are drawn between Reynolds number and the friction factor. So for example, if we were looking at a pipe that has relative roughness of E over D, then suppose it's 0.002, and you have a Reynolds number of 10 to the power 5. So you will find that Reynolds number on the x-axis, then go along y-axis until you cross the curve for 0.002 relative roughness, and then go towards the y-axis and find what the friction factor would be. So in this case, if the pipe relative roughness was 0.002 and you are flowing a liquid in that pipe with a Reynolds number of 10 to the power 5, then the friction factor for that pipe is 0.026. If you look at the Moody diagram, you should see that there are three zones: the laminar flow zone and the turbulent zone, and in between these two zones is the transition zone and the critical zone, and they are these bands along these between these dashed lines. So if you were using the equation for laminar flow, remember we learned that the friction factor will be a linear relationship with Reynolds number, which is F is equal to 64 over Reynolds number. But as the flow becomes turbulent, then we use those empirical equations that we talked about. So this is how you can find out the friction factor from Reynolds number and relative roughness. Now, relative roughness depends upon diameter and the roughness of the material. And on the same diagram, you will see this little table that provides you with the roughness coefficient for different materials. For example, if you were using cast iron, then the value of E, or roughness, is 0.26 millimeters or 0.00085 feet. And depending upon the material that is given in the problem, you will use these values accordingly. So let's do another example. Say if your Reynolds number was 10 to the power 6 and the relative roughness was 0.0004, then the friction factor would be 0.16 and something. At the same time, if the Reynolds number is same, but you change the pipe such that the relative roughness is 0.006, in this case, the friction factor will increase to 0.0332, I believe. So as you can see, the relationship determines what the friction factor is going to be. Actually, one of the problems you'll be doing today helps you figure out how does the friction factor change as you increase the velocity. So now go ahead and Adam will help you solve problem 7.93a, and then after that problem is solved using Moody Diagram, then he will help you. He will solve 7.94 part A for you, and then you will go ahead and do part B, C, and D, and figure out how does the friction factor change as we increase the velocity of flow while keeping everything else